So this is the second and last lecture from me. And today what I want to cover is the orbital evolution of the binary as it enters the gravitational wave stage and the merger, and electromagnetic emission during these late stages. And this is what I described yesterday. If the two-sentence summary of yesterday is that in galaxy mergers we expect binary black holes to be produced with a circumbinary disk, and the black holes would be sitting in a region that we think is gravitationally stable and is a thin disk. Now we want to follow the evolution of this system, which consists of 2 point masses and a thin near-Keplerian disk. And as I said yesterday, you can do analytical work, 0 and maybe in 1 dimension, azimuthally averaging the system. Really what you should, what's more helpful here is 2 or 3 dimensional simulations. And as I argued, well, actually I didn't fully flesh this out, but 3D simulations, of course, are the best, and especially at the last stages of the merger. Before then, we were very interested in the coupled evolution of this system. It will become clear in a second that the binary disturbs the disk, and because the disk is disturbed, it impacts the orbital evolution of the binary. So this system is coupled and has to be evolved over many millions of orbits as the binary, hopefully, as you will see, shrinks. So that can only be done at the moment in 2-dimensional simulations. So this is what I ended with yesterday. Essentially, I'm going to mostly discuss results of hydrodynamical simulations. And these simulations do 3 things. They clarify the long-term orbital evolution, answer these questions. Do the circumbinary disk represent an obstacle to merger, or does it help the merger? And if it's the latter, can this happen in less than a Hubble time? As I argued, you can get to this stage where the 2 black holes are sitting in this sub-parsec separation. You can get there within a Hubble time, but then this last stage is the most interesting for gravitational wave sources, and we want to know if it's quicker than Hubble time. Also, in more detail, how much time the binary spends at each separation as it evolves is very important, because when you look on the sky, if a binary spends a long time at some particular separation, you have many such binaries on the sky. If it zooms very quickly through some particular orbital separation, those sources would be rare. So it affects observations through just a lifetime as a function of orbital separation. Then, of course, we're interested in electromagnetic signatures. The basic questions are, is there gas near the binary, meaning reaching close to the black hole, tens or maybe 100 Schwarzschild radius, where we think strong, bright emission can be generated? And if so, how does this accretion happen, and how does it differ from a single black hole? This, of course, affects the observations through just the total luminosity, how bright is a binary, but also the light curves, how does the brightness fluctuate over time, and the spectral shape. Lastly, if the gas is there and impacting the orbit, is that important for gravitational waves? Can we actually detect the presence of gas this way? That's the optimistic view. Or the pessimistic view, does it mess up your gravitational wave data analysis? And actually, the secret 4th bullet for me is that this is just a cool physics problem, because it looks so simple. You have 2 point masses and Keplerian gas. So the simplest way to state this problem is almost like a textbook problem. Just 2 point masses with a Keplerian disk. What happens? Okay. So I should just speak in general that the history of this field in simulations of binaries goes back maybe 30 years. Initially was motivated a lot by planets, protoplanetary disks. And essentially it's the same thing, 2 point masses, a star and a planet with the disk. Some people are interested in binary stars. And maybe 20 years ago, this literature evolved to cover black hole binaries in this context that we're discussing of gravitational wave sources. And there are tens of 5 to 10 groups in the world doing this, and lots of papers by now. So I'm going to avoid, I'm not a numerical person. My collaborators wrote some hydrocodes. So I'm not going to spend much time on the hydrodynamics. I just want to point out that, as you'll see in a second, because the motion of the black holes is very supersonic, you expect shocks. You need a code that can handle shocks. And what we're then doing is solve the fluid dynamics equations in 2 dimensions, vertically averaging in the z direction, which is again fair as long as the disk is quite thin. Now we have to have some viscosity. In real disks, as you probably are aware, there are magnetic fields which generate turbulence and help with viscosity, help transport angular momentum of the gas outward. As the mass flows in, angular momentum flows out. But this simplest code is just hydro. There's no magnetic fields. So you parameterize the viscosity with some parameter, which tells you essentially the time scale on which you transport angular momentum outward in units of the orbital time. Now, thermodynamics is important. So these disks, as you'll see, are perturbed. They have shocks. So they're heated due to viscous dissipation. If there's viscous shear between 2 adjacent flow lines of gas and they have viscosity, they will dissipate and generate heating, which can heat the gas. Shocks also heat the gas. And then another thing, again, I could give a long lecture on accretion disks. I don't want to do that. But generally, these disks are very, very optically thick, which means the energy that you put into the gas through shocks or viscosity gets thermalized, and it's just black body emission to 0th order from the bottom and the top of the disk. So that's how the gas cools. I should say an advance maybe 15 years ago was that the black holes are actually on the grid of these simulations. Previously, most work numerically excised the actual black holes and just put a potential, a quadrupolar potential of 2 point masses, and then simulated the gas outside the orbit of the binary. Now most groups now have the black holes on the grid. And then you start with some initial steady state situation. You put 2 point masses. It's important to go out to a relatively large radius so that boundary effects don't propagate from the outer region of your simulation to your domain of interest. Then, because this is 2D hydro, you can run for tens of thousands of binary orbits. You can observe the system settle to some kind of steady pattern. Then in this setup, there are really only 3 interesting physics parameters. One is the mass ratio, black hole 1 versus black hole 2. That's called Q. The eccentricity of the binary, which E. And then the disk temperature initially, or the equivalently the aspect ratio H over R. Oops. And I don't know, I don't want to go into the details here, but if the gas is cold, the aspect, then the disk will be very thin because it's supported vertically by the pressure. The colder disks are thinner. So this disk temperature is equivalent to the aspect ratio of the disk, height divided by radius, or equivalently the Mach number. That's actually, that's an important point, is that generally the sound speed, the temperature of this disk is low, so the sound speed is much slower than the orbital speed of the gas. Very prone to getting shocks. In a single black hole disk, there are no shocks. There's nice laminar flows, and slow accretion of the gas inward. So that's it. This is the setup. I have lots of cartoonish explanations. Hopefully that's actually more useful for this crowd. So first I want to focus on the most interesting parameter, which is this is a typo. Q should be less than 1. M2 is the secondary, the lower mass. M1 is the primary, the higher mass. Q is M2 over M1. And then this is our problem. We have a disk and 2 point masses. And as I said, this field goes back, has some lots of work done on it, mostly in the literature on exoplanets or planet formation. So this is a regime where this is Earth and this is Sun. So the companion black hole is very light compared to the primary, less than 10^4. The planet people call this type 1 regime. This is a regime where the ratio is maybe 10^4 to a few percent. This is called type 2. And you can see the main thing is this gap. And then this is the regime that has no particular name because there are no planets much bigger than, I don't know, 1% of the mass of the star. That's the newer regime. The behavior is quite different in these regimes. And of course, we're mostly interested in these two, although this is also a very interesting gravitational wave source called extreme mass ratio in spiral. It will probably come up if it hasn't already. And let me say a few words about the physics of this orbital evolution of such a system. So the first one is type 1. This is called type 1 migration. This is in some ways the simplest, because here you can actually do theoretical analysis, because the mass of the perturber is so small. This goes back to a paper by famous paper in 1980, where you put a perturber in a disk and maybe focus on this middle panel. What happens is you have linear perturbations. You can actually decompose, you can write down the fluid equations, and you can do linear perturbation theory, and you can obtain the torques which are deposited at resonant locations. Whenever the gas orbit is an integer ratio, rational integer ratio with the orbital time of the perturber, there are resonant locations, and you make stronger perturbations there, and you form these spiral arms, and you can do a linear calculation of the resulting torque, meaning these non-axisymmetric features will impact the orbit of the gas, of the perturber. And it's linear, so you can actually derive a scaling. For example, the torque goes like the perturber mass squared, because its mass is linear in mass, and the perturbations are also linear in mass. So the net result is that the migration rate goes like mass. This regime is, however, complicated because you have to do thermodynamics, which impacts the detailed shape of the torques, which mostly are coming from here. So what you assume about cooling and heating has a very strong impact, and this has been a lot of discussion in planets, whether this migrates outward or inward. You can actually change the sign if you change the thermodynamics, meaning cooling time. In the simplest way to say it, cooling time divided by the orbital time. If you change that number of the gas, you can make this go inward or outward. I would say this is still not 100% settled because realistic thermodynamics is hard, but its migration rate can be quite rapid, meaning for cosmological timescales, it's going to happen millions of years. So this is, on the other hand, the sign is not 100% under control. Okay. The second regime, it's useful to, picture from Wikipedia for the next regimes, just in case you're not doing dynamics. If you have, this is the sun, this is the moon. In our case, this is two black holes. And this is in the co-rotating frame. These are the streamlines or orbital. If you put massless test particles, they will follow these orbits. So out here, the test particle will go pretty much on an undisturbed circle. Then around the perturber, there are also undisturbed circular orbits. They're bound to the perturber. And then in between, this annulus is called the Hill region, where the tidal force from the sun is comparable to the gravitational pull to the perturber. So here the streamlines actually go so-called horseshoe orbits. The gas tends to come in here and turn around and make something called a horseshoe. If nothing happens, if there's no viscosity, it will just vibrate like that. There's also Lagrange points, and gas can circulate around those points. This is a 30-second summary of dynamics around two-body system. Okay, so in this next regime, which I call type 2 here, the perturber is more massive. Picture there. So what happened is, if you look on such a disk on the side, you open a gap, a gap which corresponds to this Hill region. And the reason you open this gap is that if this happens, if you satisfy two criteria. One is what I just said. The perturber is massive enough that its Hill radius, which is the width of this annulus, becomes wider than the height of the disk. That means you basically don't have a stable disk, circulating gas in a stable disk above and below, and you just open the gap. The second criterion based on viscosity. If viscosity is very strong, then gas from outside can flow in and fill this gap. So the mass ratio has to be higher than some value, which has to do with viscosity. That this gap, essentially, a simple way of thinking about it, if neither viscosity, if the time it takes for viscosity to close this gap or pressure to close this gap is longer, is too long, then longer than the time it takes to excavate this gap, then there's a big gap. In this regime, the notion was, actually maybe I'll skip details here, but the migration is very different. To zeroth order is a barrier here. And you can think of this perturber as a particle in this disk. So if this disk is slowly viscously accreting towards the primary black hole, which is sitting here, this whole gas is radially slowly falling towards the primary. You can think of this as just a particle that's locked in the disk. So together with its gap, it's just moving in on the viscous timescale. That's a zeroth order prescription. Maybe I'll skip the corrections to this. This is also interesting because this is always inward. This is helpful. This system is trying to coalesce. And the viscous timescale is generally quite short also. I won't go into the details, but also, let's say, tens of millions of years. In an accretion disk, we think surrounds galactic nucleus, black holes in galactic nuclei. This would be a rapid inward migration on roughly the viscous timescale. Now we come to the third regime, which I think is the most interesting, most relevant, because we expect most galaxy mergers to produce binary black holes which are more equal mass. Actually, the result of, maybe I won't go into the details of that either for now. Now, if you have a more equal mass binary, then there used to be a cartoon. So again, this is the regime that was not simulated by planets. So relatively newer. There was some notion, particularly from this paper, 2005, that if you have 2 point masses, it will not really allow accretion because there are no stable orbits in this entire region. And the tidal forces from this binary are so strong on the gas that it will make this cavity. In fact, maybe I can just describe this now. There's actually a very simple thing you can do. It was already done in this paper by Paczynski 77. You can ask the following question. If I have 2 equal masses, and I put a massless test particle, are there stable periodic orbits at some particular distance from the center of mass? The answer is that roughly twice the separation of this mass, there are stable periodic orbits here. If you have a massless test particle, it will happily circulate. It will not be an exact circle, because it will be deformed, but it will be going around. If you put a test particle anywhere here, it's going to go berserk. There are no stable orbits. They'll be ejected. And within one orbit of the binary, they'll be ejected. That was the cartoon picture. But if the binary cannot accept gas, and the gas is flowing in from larger radii, there will be some pileup here. That was the idea. Now, simulations, yeah. Yes, in fact, this argument is correct for dark matter, but is, as I show, incorrect for the gas. But for dark matter, it should be completely correct. Well, actually, let me fine-tune that. So, say something more in the next slide. So, this is a summary, but now these are hydrodynamical simulation results. You just see the surface density of the gas around different mass ratio binaries. And you see here, this is 10⁻3. So I'm not showing the very low mass perturber regime, it's just linear perturbations. You make the mass 10⁻3. This is after 100 orbits of the binary. You see it's starting to form this gap. This is 10⁻2. There's a very strong gap. But what you should notice is still very symmetric. And this is 0.05. This gap is now become very distorted and trying to look like a cavity. And this is the equal mass case. So this is the most interesting one I'm going to focus on mostly from now on. But you can see here what happened. There's a cavity. It's not true that there's no gas in here. In fact, there are two small disks on the individual black holes. And there are these streams of gas which seem to penetrate this cavity. And if you do the test particle argument that I just went through, you can actually understand most of this. So this is actually my former student. 10 years ago, we did this fun calculation. You can do it. Could have been an exercise for the class. You just put massless test particles around a two-point mass system and follow their orbits. And what we have done here is we I don't know, a bunch of each one of these is a massless test particle, and then blue and red and green are marked based on whether in the restricted three-body problem these particles. Okay, back up for a second. In the restricted three-body calculation, where you have massless test particle in the binary potential, no conserved angular momentum. There's one instead of two. There's one conserved quantity. It's called the Jacobi constant. Kind of like an energy, but it's for a two-body system. And based on that argument, which I want to go into the details, you can actually tell if you put a particle here, by energetic argument, it can never enter inside. Red particles mean, we know before doing any orbital integration, the red particles can never come out because of energy conservation, or Jacobi constant conservation. The green means we don't know. Those particles can go anywhere in principle based on their energy. So then you run these particles for about 100 orbits of the binary, and you see indeed all the blue particles stayed out, red particles stayed in, as we already knew, and here the green particles also stayed where they were. You make the mass ratio higher, 10⁻3. This is where this gap's starting to open, and you see the green particles now got evacuated from this Hill annulus. And if you make the mass ratio 1%, now you see the test particles. This is the Hill annulus. The test particles are completely ejected from here. In the equal mass case, they're completely gone. And just one detail here. First of all, as I said, this actually, you could think of this, if you want, as dark matter. This could be a simulation, and this could be dark matter particles. Somebody is interested in dark matter. Now, the red points would remain bound to the individual black hole. They can happily survive here, but in the bulk of this cavity, they can't circulate in a stable fashion. They're ejected. The last thing I want to, then we can move on, is that, have you heard about Trojan asteroids? So if this was the Earth and this was the Moon, this is the Lagrange points, and there, in fact, you saw in this picture I showed, that there exist orbits like this. They librate around the Lagrange points. They're ahead of the orbit of the Moon and behind the orbit of the Moon. So likewise here, you can reproduce this very easily with test particles. There will be particles going around and remaining around these Lagrange points. So this is very interesting because these, you can show in the stability analysis that these orbits only exist if the mass ratio is less than 0.05. you make the mass ratio bigger than 0.05, more equal, there's no stable orbits at all around these Lagrange points. And what this means is that the gas that's trying to accrete undergoes a very different behavior. Below this mass ratio, the gas, if this was the gas, coming in on a viscous time scale from outside, below this mass ratio, let's look at here, it will enter the gap. And then very quickly go through the gap, so there is a very low density region, but the system is very stable. If you make a movie of this simulation, it's a still image. It just looks like this, because the gas keeps in the co-rotating frame of the binary. The gas comes in, and then it stable librates on this horseshoe orbit, but then eventually ends up going through and going onto the primary. Very stable, there's no time variability. If you go to 0.05 or higher, you lose this stability. The gas is trying to come in, but there's no stable libration to go through the gap, so it's going in all random chaotic directions. The system becomes very unstable. This is very critical for finding binaries. Below a mass ratio of 0.05, the accretion is very stable and looks like that. Above 0.05, it's very unstable and time dependent. These are actually movie versions, just so you can contrast. Oops. This is not playing. This should be. So these are the movie versions of a 1% mass ratio, 0.05 and 1. It's just nicer. These are in the co-rotating frame. This you can see the black hole also circulating. You see it's very stable. This is becoming quite unstable, and the main point here is that you feed the binary even though they're this large cavity. Now, this is important both for orbital evolution and electromagnetic signatures. Let me just summarize what I've said, and now focusing on the equal mass case. First of all, there's the central cavity. That's explained by lack of stable orbits. Density is very low. Very interesting fact is that this cavity is not circular because of this. This is another version of this movie. Anyway, I think you saw the movie. This is a very dynamic situation. Every orbit, you peel off these streams, which enter the cavity, and some of it is flung back out and hits the wall of this cavity. So this shape of this thing becomes very non-axisymmetric, and there's a dense lump which goes around. This lump is important because it modulates the accretion on a time scale that's different from the binary's orbital period. These streamers, also I like to emphasize, they enter the cavity, but you can ask, why is this binary accreting? In the test particle limit, the particles are just ejected. Well, the reason it's actually able to pull gas in from the cavity wall is shocks. Pull the cavity in, you pull in some gas, it undergoes some shocks, angular momentum can be transported out by the shocks, and the gas can come in. This is very different from single black hole accretion, where the angular momentum transport is because of magnetorotational instability. And here, this has nothing to do with that. This is just sloshing around the gas and making shocks. That's how the individual mini disks, we call them, are fueled. Most importantly, for electromagnetic signatures, these mini disks periodically appear and disappear. I think you should watch the movie one more time. But for some reason, I can't show the movie. Okay, you have to believe me, it's very dynamic. For this mini disk, fueled and then they're gone, they reappear again on the orbital time scale. Skip this. Oh, let's skip this, I said enough. Well, I'll just say this because this is another thing you could do in the afternoon. This is the positions of test particles to try to explain these streamers. you take an equal mass binary, you put a bunch of text particles, which you can't resolve by eye because they're just black. And then you do a quarter orbit, half an orbit, three-quarter orbit of the binary. Look on the co-rotating frame, so the binary is always sitting horizontal. This is what happens to this annulus of particles. This just demonstrates that the tendency to form these streamers is extremely trivial physics. It's just the binary potential distorts the gas like this. It tries to remove angular momentum in these quadrants from the gas and makes these streamers. Of course, these are test particle calculations. So once the orbits of the particles cross, you have to throw them away because gas will then shock instead of particles going through each other. But again, if you want this to be dark matter, dark matter will actually do this. But it's very clear that in the simulations you see the hydrodynamics follow this kind of forcing of the streams, but then you see the arrows show the streamlines and velocities, the velocity field. You see form the shocks. Because of the shocks, this stream continues these individual black holes. So this is great news because if you want to discover a gravitational wave source and you want it to be bright, that's fantastic news. You can actually fuel the sources quite efficiently. In fact, maybe I'll just give away the punchline already. When you measure in the simulation the accretion rate coming in through these streams and accreting on the individual black holes, and then you replace the simulation with one black hole, you find the same accretion rate. This propeller, the binary propeller, is very efficient in creating this cavity, suppressing the overall density, but it doesn't do anything to the ability of the gas to enter and accrete and be captured by the black holes. Now, what is the evolution of the orbit? So this description I just gave is sort of an overall view, but now we want to ask a more stringent question. How does the binary evolve? And when I say how does the binary evolve, I mean the semi-major axis. Does it shrink or expand? Do you develop eccentricity of the binary? And then what's the accretion rate? So how does the mass grow over time and the mass ratio, or equivalently M1 and M2, how do they grow over time? So we can answer all these questions from the simulations, but I like to ask a question, just for fun. Do you think the semi-major axis expands or shrinks as a result of having this stuff surrounding the black hole, so it's not in vacuum? Do you think the presence of this gas expands the orbit or shrinks the orbit? Now, if you think it expands the orbit, raise your hand. Somebody got very disturbed. How about you think it shrinks the orbit? Anything else? Very good. So correct answer is yes, it depends on the hydrodynamic quantities. But I like this question because it's so simple, this setup, and the answer actually is quite hard to get and is not trivial. And now I want to explain why is it hard to get the answer and why it took only 5 years ago we actually know the answer to this question. And that's because there are two sources, two reasons you change the orbit of the binary. One is just direct gravitational forces. You have all this stuff around the binary. Each fluid element has a force gm over r squared on both components. So now you have forces acting on the which are from external material, and that changes the orbit. Pure gravitational torques. There's also accretion. The black holes accrete. They accrete both mass and momentum. Accreting mass and accreting momentum both change the orbit. First point is that when you actually do these simulations and you measure it, the gravitational torques generally are quite dominant. So you don't generally have to worry about accretion. The accretion is slow over the viscous time scale, which is be hundreds of thousands or millions of orbits. The gravitational forces you have to sum over. And now the reason this is so subtle is that the gravitational forces from the gas come mostly from very close to the black holes. And what's shown here, this is an example of the equal mass binary, so just ignore the bottom. This top part is a simulation like the one I showed, and it's time averaged. Because the system fluctuates so strongly, and you're interested in not necessarily instantaneous forces, but long-term evolution, you average over, let's say, hundreds of orbits. This is the surface density. And this is the torque density. This is the color bar. So yellow here means high density, black is low density. The gas is evacuated, and there's a beam here. And this is torque density. This is the color bar. Green means that the torque is positive, means, so these black holes here are moving counterclockwise. This is in the co-rotating frame. We averaged the gas distribution. These are co-rotating, so this green stuff here is ahead of this black hole, the purple is behind. So dark green means it's pulling the black hole forward very strongly. Light green means it's pulling forward less strongly. This is a torque surface density, so torque per unit disk surface area. Purple is the opposite, it pulls back on the black hole and is trying to remove its angular momentum and make it in spiral. Green is trying to make the binary out spiral. Purple is trying to make it in spiral. And now you see the problem is that if you do this by eye, and you have to do a two-dimensional integral of this quantity that's shown here, but the sign of this is positive and this is negative. And if you try to do it by eye, you can't tell whether it's positive or negative because the cancellation is almost perfect. Okay, so this I find very interesting because there is no theoretical explanation what this integral should be. No, as far as I know, there's not even a good approach to try to answer this theoretically. So instead, what happened in the field is that we got together in 2022, that's not after this paper, and about 10 different groups did exactly the same test problem with 7 different codes. Everybody got within factor of 1.5, the same result. So at least we know numerically the answer is correct under these assumptions. We have no theoretical explanation, but you can see by eye that this is not, there's no back-front symmetry. There's actually slightly more green stuff than purple stuff right here. And when you do the integral, this particular binary is out-spiraling. Net torque, which is much smaller than the absolute value of either the positive or negative. The reason it took so long is you have to do simulations which do many orbits, so you can time average, but has to have very high resolution to get correctly the shape of this stuff. So the current understanding is, at least in this toy model setup, is that a vanilla binary would out-spiral, and the gas would be an obstacle to the merger. And that was kind of a problem, or let's say, if you want to find gravitational wave sources, then you can start worrying or panicking, because that means the gas doesn't want the merger to happen. Now, it turns out that that was actually an artifact of everybody doing simulations of a relatively warm gas disk. As I have to emphasize, this disk here has an aspect ratio of 0.1, which counts as extremely hot and puffy in the field of quasars. Real quasars, AGN disks, have aspect ratios of more like 0.01 or 10⁻3. They're very thin. This we know from theoretical models fit to observations of spectra of quasars. The problem is those are much harder to simulate because the gas is colder. Features that you get are much sharper in the simulation because pressure is lower. You have to have higher resolution to capture the features correctly and smaller time steps. That has been a challenge. But in this paper, we just show that even if you make the disk temperature 3 times lower, approaching more closely what we think is a realistic cold disk. In fact, you flip the sign of the torque. You can actually see by eye, for some reason nobody understands, when you make the disk colder, you see more purple stuff here compared to here. This stuff is pulling the black hole backwards and causing it to inspiral. So now we understand that the cold disks tend to inspiral, and the time scale tends to be essentially the accretion time scale. So A over A dot is the time scale on which you shrink the semi-major axis, comparable to M over M dot. M dot is the feeding rate of this disk from some larger radius, which is feeding the two black holes. So now that time scale again for bright quasars is tens of millions of years. The mass doubling time of quasars based on how luminous they are and how big the black holes are. That means in tens of millions of years, in principle, this black hole would merge. That's good news. Okay, now somebody asked about eccentricity yesterday, and there's another interesting result, again, numerically converged, which are not explained by theory, which is that this binary is actually become eccentric due to the presence of the gas. This top panel here is a suite of simulations where we measured dE over d log m. So this is essentially E dot over M dot. So for every gram of mass you accrete, eccentricity is changed by dE. And this is 0, so this is a circular binary. This is 0.85, this is a very eccentric binary. This is positive, that means the eccentricity is increasing. If you were to start with a nearly circular binary somewhere here, dE is positive, so it would move to the right up to this point. Start with a very eccentric binary. This is negative, so it would also move to this point. This point is an attractor, roughly 0.5. That means the gas tends to create a binary that has an eccentricity of 0.5. Unless it starts extremely circular, 0.1 or less initially in eccentricity. This is negative, so then it becomes circular. So roughly speaking, if you have a precisely circular binary that's formed somehow circular, surrounded by a disk, it will remain circular, but generally all the binaries will be driven to 0.5. So A tends to shrink if the disk is cold. E tends to go to 0.5. Then the mass grows at a rate that's essentially the outer feeding rate. The binary is not blocking anything. And then the mass ratio is the last interesting question. And that result is actually not new. People who worked on stellar mass binaries asked questions 40 years ago, why are massive stellar binaries tend to be equal mass? Basically, the result is that the lower mass black hole tends to accrete faster than the higher mass black hole, and in an unequal situation. So this shows M2 dot O, the rate of the rate of increase of the fractionally of the secondary divided by the primary, M2 dot over M2 divided by M1 dot over M1. This is a test particle limit. This is the equal mass binary. For equal mass binaries, this number is 1. Time average, they accrete the same. But if you make, let's say, a binary that's mass ratio is 1 to 10, you see that the lower mass guy is 100 times faster accreting. So we'll tend to catch up with the primary. That means gas disks force the binary to become eccentric and equal mass and spiral inward. There's some observational confirmation of this from stellar mass binaries, but I'll skip that. This is the upshot. Question? I throw my hands. I don't know. Again, it's dominated by gravitation force, direct gravitation torques, and well, and for radial forces. There's no explanation. So yeah, so that's very interesting because there are complications. For example, the mass ratio also there's mass ratio. So yeah, the binary can actually make a U-turn because the sign of A dot not just depends on temperature, it also depends on eccentricity and mass ratio. I just didn't want to go into all the complications. But yes, you can make a system where, let's say you start with very unequal mass, it's spiraling in, and then it goes up to some value, and then it makes a U-turn, starts to go out. There are different evolutionary paths implied by this fish model. That's very cool. Yeah. But ultimately, they're driven to, if they're driven to this state, they will actually in spiral eventually. So now comes another last point, which is once this, so let's say we have this in-spiraling binary, it's eccentric, it's grown to roughly equal mass, but then it reaches very small separation, roughly 100 Schwarzschild radius. Here the key point is that the gravitational wave emission will take over. The in-spiral rate caused by gravitational waves, I think I already said this yesterday, the point is it's a very steep function of separation. The power in gravitational waves is a to the fourth. A over A dot is actually goes like the cube to -3. That's much steeper than this gas-driven evolution as a function of separation, which means there will be a point at which gravitational waves completely take over and accelerate the in-spiral, and you get the merger. And I will return to this point, because then you have to worry about what happens to the gas. I'll return to that point. Let me just summarize. Actually, I think this will be useful summary. Let me show this cartoon summary. I made this part a bit complicated, but it describes this global view of evolution of binaries. So here is the frequency, or equivalently the orbital time in years. So here the orbital period is 1 year, nanohertz. This is millihertz here, the orbital period is hours. Binary starts large, wide, so they start on the right and they try to move to the left. These are different equal mass binaries, 10 to the 3, 5, 7, 9. This one is the gravitational wave in spiral, which I just said is very steep. This curve here is returning to my summary yesterday, that stellar scattering can initially cause the binary to shrink its separation. But especially for massive black holes, it becomes very, very slow. This is stellar scattering-driven decay. The unit on the y-axis is the time spent at each orbital period. For example, here, this is in units of 10 to the 7 years. That's because, because quasars live for 10 to the 7 years. So here is the Hubble time, 10 to the 10 years. And then what you can conclude here is that with just stars and gravitational waves, these very low mass binaries would actually merge in less than Hubble time, but will be hung up for billions of years. The 5 solar mass would be hung up at this bottleneck for 2 billion years. And these massive ones would never merge. And then when you put in the gas, the effect of gas from these circumbinary disks, you basically get this regime. So for example, let's look at 10 to the 7 solar mass. Initially, it's given shrinking due to stars. Then it goes through different stages of the disk. then quickly shrinks, and then gravitational waves take over. This is the picture you should go away with. I think binaries can merge in the Hubble time. The merger is quicker for lower mass, because gas can push it faster, and at very large separations, it's stars that help you drive together the binary, then gas, then gravitation. And just for reference, this is the LISA band, so millihertz. This is pulsar timing, nanohertz. And there's a couple of interesting points, which return to my third bullet in the introduction. You see that the gas is important still, because you're at this breakpoint. So gravitational wave and gas is equally important for very low mass LISA binaries. In the pulsar timing arrays, this is 10 to the 9 solar mass binary. And it's actually transiting from gas-driven to gravitational wave-driven at around nanohertz. So that's very interesting, because that means when you're observing the nanohertz gravitational waves, these binaries that are sourcing it could be affected, or the unity, by the presence of gas. And then electromagnetic surveys, which I'll get to soon, are sensitive to orbital periods of, let's say, days to years, where we can monitor objects and try to find the binaries whose periods are days to years. So that would be here. And in between this, slightly overlapping with both gravitational wave regimes. Okay, so that was the orbital evolution. Now let's switch to the other question. What about the electromagnetic emission? What do you expect to happen from binary black holes surrounded by circumbinary disks? And in particular, how would they differ from a quasar? If what we're talking about here is, going back to my motivation yesterday, gas is very efficiently fueled to the center. The binary accepts it, so it's like a quasar. It should be very bright. How does it differ from a single black hole quasar? And then the three both categories you can think about. Well, this equal mass binary is, as you saw in the movie, is very strongly fluctuating. So there will be different from a quasar in principle, because there will be periodic fluctuations. Spectrum will be different, because as opposed to single black hole accreting through viscous dissipation, here there are all these shocks which provide extra heating. And you can imagine it will cause the spectrum to be harder, because you heat the gas to higher temperatures. And then if there are emission lines, they can be distorted in their shapes and also moving offset in velocity, because the gas is moving due to the orbit of the binary. I should emphasize that in general, you can have two completely different exercises in mind. You can say, well, I've detected already a gravitational wave source, which I won't actually get to it in my lectures, but LIGO detected already gravitational wave sources. So if this was a stellar mass binary, you could try to find the counterpart of that particular gravitational wave source. LISA will be extremely interesting for this, because sources in the LISA band will live for weeks or months or even years. You have a lot of time to poke around in telescopes and try to find counterpart in electromagnetic observations. But you could also try to find these binaries irrespective of the gravitational wave emission. Just look at electromagnetic surveys, try to identify binaries, and generally they'll be wider, longer period sources, but they'll be progenitors of the gravitational wave sources, so you can understand the population if you can measure the population in electromagnetic surveys. So I'm worried that I have too many cartoons. I think I'll skip this, because this will be too long. I don't know if people here are quasar experts. Yeah. Aside, I wasn't going to talk about this much, but I think it might be more common to produce jets. So cosmic rays are produced, we think, has to do with particle acceleration in jets. It could also be magnetic reconnection. Jets, I think, can be very frequent in binaries because jet production is associated with accretion that's very sub-Eddington or super-Eddington. If you know what I haven't defined Eddington, but the accretion rate for the black hole mass is higher than this critical value called the Eddington limit, or very much below, then you tend to have jets. And in the binary, I think that's going to be very common. Unless you fine-tune the accretion rate and make it very equal mass, one of them will be sub-Eddington or super-Eddington. Think about it. So jets will be more common. So I think there will be more common sources of cosmic rays than single black hole quasars. Now, in terms of energetics, I think also could be very conducive to cosmic ray production because magnetic field lines. Another way to accelerate cosmic rays is instead of shocks in jets, it's through magnetic reconnection. And you can imagine these binaries dragging the magnetic field lines, and there's lots of reconnection possibly. There's more options to accelerate. Let's talk maybe, but the answer is it's not really well understood. I think people are probably not quasar experts, so I just want to say that we think we understand roughly. Quasars have an accretion disk. There's one black hole in the standard picture. There's a small accretion disk. There's a jet that can be produced, and then it's surrounded on larger scales by a fatter, thicker torus material that's supplying the accretion. We're mostly now talking about this accretion disk, which can be hundreds or few hundreds or thousands Schwarzschild radius. That's where optical and UV emission comes from. There are these clouds which are not fully understood. They're very close to the black hole. They're moving fast. They're ionized by the emission from here, and they emit broad emission lines. And then farther away, there are slower moving clouds of gas. So they also ionized and produce emission, and the lines are narrower. So that's the narrow line region. Narrow emission lines, broad emission lines. That's this disk. So observationally, the best, most common way to observe AGN is through the optical UV emission from this inner disk. And okay, here's one equation summary of accretion disk theory, which is if you have a steady disk, there is a accretion disk surrounding a point mass, and if m dot is steady, you have a steady state model. That means you're liberating at radius r energy at the rate gm m dot over r. M dot is constant through the disk, and that heating, that energy has to go somewhere. If it's coming out as blackbody emission from the surface, then it's sigma t to the fourth times the area. M dot is constant. This equation tells you temperature is r to the minus 3/4, which means the inner disk is hot, the outer disk is colder, and therefore this emission from this disk is a multicolor blackbody. You sum up a bunch of blackbodies. That's the rough description of optical and UV emission. The actual spectra of quasars look like that. It's actually consistent roughly with this multicolor blackbody summation. It gives you a power law which goes like nu to the 1/3. Then there are all these emission lines that I just described. Now, if you take this spectrum, it's just a factor of 3 or 4 in wavelength in the optical regime. If you have a 10 order of magnitude panoramic view of the spectrum of quasars, this is a famous compilation of average quasar spectra by Martin Elvis 30 years ago. What I want to emphasize, this is the optical region that I just described. There's also infrared, radio, and X-ray, which come from different parts of this disk. X-rays come from few Schwarzschild radius, we think, from hot electrons, which are sitting above and below the black hole here. few Schwarzschild radii. That's what's thought to produce the X-rays. And then the radio emission and also gamma ray, which is not even shown here, have to do with this jet. Now, all of this can change if you have two black holes instead of one. We have only 20 minutes left. So let me just say a couple of... let me just also point out from the very beginning, we do not have a confirmed case of a binary black hole in the galactic nucleus. We can't resolve it spatially. I will introduce some candidates. So this field is very much evolving or infancy. But these are ways you could look for binary black holes. Let's do it first without gravitational waves. So the one point I want to strongly point out that it's extremely likely that the emission will be periodic on the orbital time scale of the binary and also possibly on longer, factor a few longer periods. So if you have a random binary on the sky, which can be face-on or edge-on or in between, it doesn't matter. I've discussed that hydrodynamical modulations change the accretion rate and make it, I will show you in a second, make it periodic. If you have a binary that's not completely face-on, then this disk is moving around and the black holes are also moving around. You'll have Doppler modulations from special relativity. When the black hole that's shining is coming towards you, it will be brighter. When it's going away, it will be dimmer. That will happen generally, it's just, if it's edge-on, it will be stronger, but if it's not edge-on, it's 45 degrees, it will just be suppressed. This modulation will be suppressed by a factor of 2, so it will happen unless you're face-on. Then the most recently realized cool thing to introduce is that if you have a binary that's within a few degrees edge-on, which should happen also not super rare, then one black hole can go in front of the other and cause gravitational lensing, the general relativistic modulation of the light. Okay, 15 minutes. Let me say, yeah. So very good. I probably won't get to it, so let me answer. I have whole slides on this, but there's, maybe I can just jump to that. So I was gonna introduce all this and then say actually, maybe I will try to get to it in one slide. So hold your horses. And it's not super rare. It's 10⁻³ I will get to it. These periodic modulations are something you can look for in quasar databases and won't be super rare, but let me just say a few words about each. I think the hydromodulation I just want to point out again that this is the accretion rate. This is for a near equal mass binary. This is for a less equal mass binary. The top panel is m dot in reference of single black hole accretion rate. This is order unity, so the binary is accreting as if it was a single overall. The green and the blue are M1 and M2. You see they're fluctuating. This is the Fourier transform. And you see that they're periodic. You can actually see by eye periodic modulations on the orbital period. It shows up in the Fourier transform. There's also a strongest modulation is actually a factor of 6 times the orbital period. That has to do with this cavity rim not being axisymmetric. You see by eye, this is 5 orbits, 6 orbits. You see by eye that there's modulation on the time scale of 6 orbits. That's the gas time scale for the gas at the wall of the cavity to go around. So that's periodic. If you make it unequal mass, this is 1 to 9. The green is the secondary. It's accreting much more than the primary. The primary is the blue. That's what I said. It's actually trying to grow faster and catch up. The explanation for this is very simple. The secondary black hole is lighter, so it's displaced from the center of mass 9 times more than the primary in this case. So it's much closer to the cavity wall. It's capturing the gas. And you see that it's even cleaner than here, and it's just fluctuating on the orbital timescale, half the orbital timescale, twice the orbital frequency. So that's basically, I think, all I say for now. Just from hydrodynamics, you expect modulations periodically of the accretion rate. I won't go through it. The same modulation also exists in the luminosity. If you sum up the blackbody emission from the surface of this binary disk, you see basically the same kind of pattern. This. Actually, so now I can answer your question about how rare is this. Do we see this phenomenon? And the answer is, last 10 years, there are 3 large, so in order to look for this, you need a bunch of quasars, ideally a lot of them, which have time domain data so that you can actually look for periodicity. Now, how rare should this be? The in-spiral time of the binary, so let me just say one more thing. The surveys that exist at the moment, now we're talking about practicalities. There are surveys which exist, which have large numbers of quasars, but most of them don't have time domain. They haven't monitored large parts of the sky. Their exceptions are, one is called the Palomar Transient Factory, the other is called Zwicky Transient Factory. That should be a ZTF. There's actually a recent paper combining Gaia observations with Sloan. All of these surveys are quite shallow. They haven't gone very deep because they monitored a large fraction, half of the sky. They're pretty shallow. They only see very bright quasars, whose black holes are 10 to the 9 solar masses. And for these, we have this one, I skipped in my words. This is the largest one. It had 250,000 quasars, monitored roughly every 2 weeks. All of these shallow surveys have data which probe, let's say, from weeks, cadence to years, and go on for 10 or 15 years. So you can look for variability. Now, if you take an orbital period of 1 year, to which you're sensitive in these surveys, let's say, at that orbital period, the in-spiral time, due to the binary disk, happens to be, as I showed before, roughly the same as the gravitational in-spiral time, and roughly 100,000 years. If you have such a binary in the period of a year and mass of 10 to the 9 solar masses, you will be happily living like that for 100,000 years. Now, quasars, empirically, we know that they live for about 10 to 8 years. If you can ask me why or how we know this, but we count the quasars in the sky, irrespective of what everything I said. We just know from observations their lifetime is about 10 to the 8 years. So that means if every quasar was triggered by a merger, then 0.1% of quasars should be binaries with a period of a year at this high luminosity. And it turns out that these surveys have all roughly found the same. So, and in these surveys, this is my graduate student, you find some objects which seem to have periodicities. Indeed, about 10⁻³ of the cases of quasars. This survey has 250,000. They published a list of 111 candidates. Maria's thesis, we looked at 36,000 quasars. We found 33 candidates. And then this later, similar ratio, 10⁻³. Now, I should just end this with saying that this is very controversial and also very exciting, because it's controversial because quasars, they flicker, unfortunately. So this whole business is very difficult because you can't just take a Fourier transform and find the peak and say, I found the periodic source. In fact, I think, I don't have a picture. We understand the statistics of flicker of quasars. It's roughly a Gaussian process, meaning that at every time scale, there's some RMS amplitude quasars flicker, and you can ask the probability that it produces a periodic signal, and it's not zero. You can, by chance, if you look at 100,000 quasars, you can easily find one that looks periodic, even though it has nothing to do with binaries. It's very hard to protect against this because we don't know the noise model of this flickering to 1% precision. I mean, we roughly know its power spectrum is actually red noise turning into white noise at some characteristic frequency. We have descriptions, but it's not understood from some theory and it's not super precise. If the noise is slightly higher at some frequency of a year, the probability of accidentally creating a periodic signal is higher. It's very hard to protect. The good news is everybody, so I'm at this point forgetting my slides, but LSST is coming online. In fact, a few weeks ago. Have you heard of LSST? I really should be describing LSST in great depth. LSST will completely revolutionize this picture. I won't have time to dwell on it. You see here these shallow all-sky surveys with time domain data have hundreds of thousands, almost 250,000 quasars. LSST, you should know, is probably the largest thing happening in astronomy on the ground, ground-based astronomy. James Webb was the biggest thing in space-based astronomy in the last few years. This is happening on the ground. It's a new telescope in Chile. They built the world's largest camera. It's, I forget how many 4 gigapixel camera. And it has a huge field of view, 10 square degrees. And it's just scanning the sky every day, the whole sky. It's located in Chile. And every few days, we have a data point on every source on the sky. This is going to go on for 10 years. And the depth you accumulate will be so deep compared to these that my students, I will skip my slide on this topic. You can calculate how many quasars you'll find because these are just the shallow time domain surveys. There are small parts of the sky which have gone much deeper and no time domain data. We know the number of quasars per redshift and sky area. So we can calculate that LSST will see order 100 million quasars. So instead of 100,000, we'll have 100 million. And instead of some messy random sampling, which is every 2 weeks or in some cases worse, we'll have every few days a data point and in 5 different bands, not just one band. This will be very good because LSST can therefore find periodic sources among these 100 million quasars with shorter periods because there's so many. This number here, you saw on my previous graph, the lifetime due to gravitational waves becomes much shorter for shorter periods. But there's so many objects that you can find sources which instead of 1 year period, let's say have a 1 week period, there will be a much smaller fraction, maybe a few thousand years is the lifetime of such sources. Lower masses, the fainter quasars live longer, so maybe 10 to the 4 years. Then you find those sources, and the period is, let's say, 2 weeks, and you have years of data. So there's no way noise can mimic accidentally 4 or 5 periods in your data, but there's no way by random chance you create 20 cycles. It'll be, I think, in a year or two, we can completely forget about this messy identification of periodic quasars. Will be replaced by 100% secure detections of periodic quasars. The question is, and then you can go on and interpret, this is my gravitational wave source population, they will evolve later, you can measure their masses, etc. I think in the 5 minutes, I just want to say, okay, but how do you know that they're actually binaries? There are other ways quasars can be periodic. Let's say a jet is wobbling for a single black hole, or there's a hotspot in the accretion disk. How do you actually know you'll find some binary black holes? So that's tied to my other sources of periodicity. One is this one. So this is one of my, so I have 2 favorite other points, and let me at least in 5 minutes get those across. So one is that what I said was that there's also Doppler modulation. So suppose all the simulation stuff is wrong. There is no fluctuations for some reason. I don't think that's possible, but just forget the simulations. This is a time-averaged density distribution of gas in a 1-to-3 mass ratio binary as an example. This is actually from a surface density in the simulation, but the point is that these circles are the so-called tidal truncation radii. So if I already said that test particles would happily be bound to individual black hole components in these circles. So these test particle calculations. You see in the hydrodynamic simulation also, you basically have gas in this mini disk that appears, disappears, appears, disappears, but on time average, it fills this tidal truncated region. And now again, just practicalities. If this gas is bound to the black hole and these black holes are orbiting, then this is like a moving light bulb, and it's going to be Doppler modulated. And even if you don't believe any of my simulations, in the X-rays, we empirically know that they're coming from few Schwarzschild radius. The X-ray emission of quasars, it varies on very rapid timescales, and also from microlensing observations, some of them are resolved in a way that you can tell that the X-rays are coming from few Schwarzschild radii, so they're well within this region. That's called a hot corona. That hot corona producing X-rays will be traveling with the black hole and Doppler modulated. So I just want to now go to numerics. If you're talking about a LISA binary, or well, let's start with this one. These are the binaries I just discussed. They identified in optical UV surveys at the moment. They're candidates. The period is a year. The mass is 10 to the 9 solar masses. You can calculate the orbital velocity. It's of order 1% of the speed of light. The Doppler modulation is a first-order effect in special relativity. It goes like V over C. So you should have few percent sinusoidal or radial velocity modulations in your light curves. The emission in the optical comes from order 100 Schwarzschild radius. So they also just fit in these regions. Be traveling with the black hole. If you're talking about the future of a LISA source, the LISA, again, I don't have time to properly go through this. Hopefully you'll learn from other lectures. A source that's entering the millihertz LISA band has orbital periods of order a day or between hours a day when it enters the LISA band at 10⁻⁴ hertz. And at that point, for 10 to the 6 or 5 solar mass black hole binary, the orbital separation is of order, again, 100 Schwarzschild radius. These circles will be of order 20, 30 Schwarzschild radius large, easily fit the X-ray emission. And the orbital velocities will be 10% of speed of light, so you'll have large modulations. I think the best for that will be UV or X-ray. The great news is that this effect depends on the spectrum. So this you can actually confirm if you see a modulation that's periodic, and you find this Doppler modulation, it will be chromatic, meaning the amplitude of the modulation will be different at different frequencies, photon frequencies. To explain that, you should just think this is a spectrum. This is, let's say, the optical band. This is the ultraviolet band, and the spectrum has a different slope. So now if you Doppler shift, if you have a spectrum that's very steep and you Doppler wobble the frequencies due to Doppler effect, there'll be a large modulation influx. If you have a flatter spectrum, it will be smaller modulation. So we claim actually this paper that was in Nature is that this is an example of one of the periodic quasars in the optical. This is its 20-year light curve. It looks periodic. This is UV data. It looks a bit sparse from Hubble Space Telescope and other instruments, Galaxy, Swift, and it looks consistent with the same modulation. This blue curve is the same sinusoid, but with an amplitude that's 2.5 times bigger than in the optical, which is actually consistent with the spectral slope. Does that make sense? This object, we have a spectrum. It's a very bright quasar. We don't have time-resolved spectrum, but we have a spectrum. So we know that in 2 different bands, what should be the ratio of the Doppler modulation. I think in future this can be, of course, done for many, many candidates. Okay, now I have 2 minutes. And the last point I wanted to make is lensing. This actually is probably the coolest pictures to end with. And apologies, I didn't get to a few other possible signatures, but I want to end with this. So as I said, if the binary is relatively close to edge-on, one of the black holes can go in front of the other, and it can distort the light due to lensing. So we know that black holes, even if they're just one black hole with a disk, have very funky looking images. They look like that in computer simulations. They look like this in observations. There's a hole in the middle where no trajectories they fall into the horizon. And there's a bright photon ring. So we see, and again, this disk here is actually an edge-on disk. It's just the light is bent. This kind of features. What we asked ourselves with Jordi Davelar, postdoc at Columbia, is, well, what happens if you have a black hole like that, and one in the front, and now you're lensing the light. So now you have to process this image, and it looks even more complicated. This is the movie, which Jordi made, and here we painted the emission. So this is not a simulation. The emission is just painted for academic exercise on top of each black hole. But the ray tracing basically solves the geodesic equation. So the photon trajectories are followed accurately from general relativity. And you see the image looks very distorted. And if you plot, of course, we can't really resolve this. I mean, the Event Horizon Telescope, here, as I said, we're able to resolve 2 black holes, but that's pretty much it for now. You can't resolve any other black holes. I mean, in principle, if there was a wide binary nearby, you could actually try to resolve this image. But for now, we're stuck with, for the foreseeable future, of just integrating the total emission. So this is a snapshot of the system when it's near conjunction, 1, 2, 3. This is the flux. This is the phase of the light curve. And you see you have 2 flares. Whenever the one black hole is right behind the other, you produce a brightening due to this lensing. You can even see a dip. This dip is what got very exciting for us personally, because this dip should actually also be there if you're aligned reasonably well. Then you're trying to lens. If you're trying to lens the hole, there's no flux there, so you actually get a dip. Makes sense? So the prediction here is that for binaries which are aligned to sufficiently well that they're within the so-called Einstein radius for lensing, you'll produce recurring periodic flares with dips. Of course, the data will be noisy, but hopefully you can pull this out of some noisy data if you have enough periods. I should emphasize this is also sounds very exotic and very rare, but it's not. For the current candidates in the optical survey, the alignment has to be a few degrees. For LSST or LISA, much more compact binaries, it's okay to align to tens of degrees. So it's not super rare. Just to end on the fact that we actually have a candidate for such an object. This, I think, will be my last slide. This object is a quasar. We call this quasar spiky. This quasar is very unusual. It was found in the Kepler catalog. Kepler is an instrument that's looking for planets, transiting exoplanets. So it has extremely high cadence because it's trying to find day-long variability or hour-long variability of stars. So and in the field of view of Kepler, there's something, I don't forget, I think 100 quasars. One of them, this is the light curve. This is the light curve. This is days, so this is 1,000 days. 55,000, 56,000. This is the light curve. Is this flare? And then there's flicker, flare, and then decay. If you zoom in on this flare, This is here 30 days. The flare looks like that. And well, our claim is that this actually fits really well with the model where this sawtooth-like modulation is from Doppler shift of an eccentric binary. The radial velocity is not sinusoidal. It has the line of sight velocity varies like a sawtooth. The flare should occur along the orbit where you're in conjunction when the radial velocity is close to zero. And indeed, at that point in the data, there's this flare. It's only 10%. It's very clear. And the shape of this flare almost perfectly fits lensing light curve. This is another candidate. Again, we hope to have many, many more things in the future. I think I have to end. I think the takeaway message is that we can do this kind of exercises in the next 5 to 10 years with the LSST data. And then LISA will come online and we'll see binaries that are spiraling in for weeks or months. And we can even try to catch the periodic fluctuations in conjunction with the LISA observations. Of course, sad I didn't get to say a lot of more interesting things, but I think, hope you learned something from this. Exciting field.